previous video we saw this function c over z. This has a residue at 0 of c minus 1, and part of a result of showing that from the Lorentz series, just this term, just its coefficient, is the only one that remains when we integrate around the circle. Now what we want to show is that only this term gives us residue, so other terms like higher ones like z2, z3 and so on, they don't contribute. And so integral over the closed loop, 1 over z squared dz. In fact, let's make it k this time. Some k integer bigger than 1, e to the 2 pi I theta. Why are we doing this? Because we can pick any circle, so we're picking the unit circle and we're going around it, and we're varying theta from 0 to 1 to get it to go around the circle, the unit circle, so we can get the contour integral. Alright, so if we do dz, this is equal to 2 pi I e to the 2 pi I theta e theta, and we'll sub it in. This is I, this is I again. So this now we've used the substitution, we can go from 0 to 1, 1 over e to the 2 pi I power of k theta, and we have the dz is now 2 pi I e to the 2 pi I theta d theta, and this cancels one of the powers of k, so we get e to the 2 pi I k minus 1 theta. We can actually bring the 2 pi I to the front, and we just have this d theta bit left over. I always find it a bit weird when people write d theta over here instead of like here, like it's like a fraction or something, but yeah, let's just write it like here. Okay, now it doesn't seem like this is very easy to integrate. Let's just simplify this a bit more. From 0 to 1, e to the negative 2 pi I. Okay, so the only thing we care about is what does this shape do? What does it do? And if we actually draw it for this function, it will go around the curve k minus 1 times. And k is bigger than 1, so it will go around the unit circle at least once. In fact, we'll go to k minus 1 times around. Now, what an integral does is basically sums up. And so if I'm here, the sum won't be 1, but will be 0 still. If I go like halfway or something, then the sum will be the average of all these points. So it would be somewhere around here or something like that. It would average these points. But if I go all the way around, the average would be the middle. And if I go around again, then the average will still be in the middle. And no matter how many times I go around, when I get back to this point, the average will be in the middle. And that's kind of the intuition for why this term, as long as k is bigger than 1 and we're going around the circle, or less than 1, the case that it's less than 1, it means that this is a positive number, would give us the case where it's 1 z squared. When this is 0 and k is 1, then in that case we have that special thing where we have the residue, right? And so for this case, because it goes around and we get the average, this entire integral becomes 0, and we have 2 pi I times 0, which is 0. Okay, so we're done. So we've shown that the residue for z to the k is residue at 0 is equal to 0 for k greater than 1. So we're done with this, and in the next video, now we kind of know what the residue has to do with this. We're kind of ready to do that problem, because we now know what we're looking for. We're looking for the term that looks like this. We're looking for the little power, and then once we've got the residue, we can work out, using the residue theorem, we can work out the sum of the two integrals, and then we just have to show one of the integrals goes to 0. Well, the remaining integral has the residue times 2 pi I. Okay, so I'll see you in the next video.